So good evening, everybody. Good evening, everybody. Welcome back to the page. It's Chris Kirwan here with Astronomy by the Bay. Just want to be sure that we're live on both feeds here, first of all, before we get started. And there we are. Okay, so good evening, everyone. Hopefully you had a relaxing day today. I'm sure a lot of you are going to be out shoveling, hopefully not till tomorrow. The storm was quite a doozy, I guess, here. We picked up probably close to 40 centimeters, I would say. But anyway, we're going to try to sit back and relax a little bit tonight and do a little bit of investigation on the night sky, a little bit of talk about the night sky. My idea here is to hopefully share some information for beginners. It's called an introduction to the night sky. I've offered this type of presentation a couple of times in the past, but I've modified it a little bit with some other slides and things this evening. So let's hope it all goes well. So let's get started. It's going to be about a 90-minute presentation. I am watching your comments on YouTube and Facebook both. Hello to Lisa, Mike, and Jamie, and hello Harold and Maggie. Good evening, everybody. Best way to stay safe, I guess, is to stay inside, and the best way to stay inside and relax is to listen up. Let's have some fun here. Okay, so this is called an introduction to the night sky. I'm going to talk a little bit about, for those who may not know me, and I know this is recorded for later, so my name is Chris Kirwan of Astronomy by the Bay. I am located here in St. John, New Brunswick. I am an amateur astronomer that loves to set up my telescopes to offer outreach and offer views of the night sky and all of its treasures to everybody that's out there. My regular place of setting up was at Saints Rest Beach, of course, just before the pandemic. And at this point in time, we're hoping that things are going to come back again, where we're going to be able to get out and share our views again once more. But at the moment, it's still unsafe, and they're telling us, to basically all across the country now, no one is doing any outreach events in person. We're really hoping that this pandemic comes to an endemic very soon, and we'll be able to get back to our public outreach events locally, of course, and also through our Star Party events, which take place throughout the province. But in the meantime, we have to continue to offer out online as we can. This is us a short while back. It seems like it was forever, but about 2 years ago, I guess, when we were set up at St. Rest Beach, and some other local astronomers would come along and join me, like Mike Bowell and a few others. And we were offering views of the moon and Venus and whatever we could offer to anybody who came by. It's a very popular spot. I get lots of children that come by too when they're interested in the night sky, so I try to share as much as I can with them as well. We also have this ability. I mean, this is something new now with technology that we can offer a smartphone sitting on the eyepiece, and it gives you an opportunity to take your own picture of the moon and take it home. You can zoom in. We can talk all about it that way. And of course, that's what I do with my live feeds as well. So, and of course, when I get the opportunity, there's little ones like this that I get a chance to set up for. This is a small brownies group offered in the east side. So every once in a while, that gets to happen too. So that's a pleasure. And of course, this was my setup just a couple of years ago. I did a few on in-classroom presentations last year, but not very many because of the fact of the pandemic. So my setup is more like it is there on the bottom, and I just offered 3 classroom talks this Thursday and a couple of last week, so it was great to be able to do that at least. Good evening, everybody on Facebook and everybody on YouTube. Thank you all for joining me. So we're going to get into a little bit of the talk about, of course, our Sunday night astronomy show is something else that we offer with these 2 guys here that are my best buds as far as astronomy guys go that get me along through the show, and they certainly carry me through the show for sure. Our topic tomorrow night is going to be discussed tomorrow morning. You'll see, watch for our post, but we're on 8 o'clock Atlantic Standard Time every Sunday night. Now, about us. Well, I belong to the St. John Astronomy Club and the Royal Astronomical Society of Canada. I'm part of the New Brunswick chapter. We have about 100 members here in New Brunswick. We have about, I guess, probably 30 to 40 members in the St. John Club. There are 3 clubs around the province. And our regular activities, well, we have regular monthly meetings normally. In an endemic year, we would, to discuss the night sky and share a common interest through talks and observing. We do lots and lots of outreach. I've done a lot of it myself. We volunteer, of course, through presentations of night sky observing through our telescopes while visiting schools, youth, and special interest groups. We offer star party events at the designated dark sky parks in this year. We have those dates already set. They're all listed on my page just a short while ago. And we're really hoping, fingers crossed, that we're going to get to some of those events. Those are excellent to take part in. I suggest that you go back and take a look at the Star Party event dates, or you can go to rasknb.ca. They're on there as well. And they'll also, you want to be able to book your campground site ahead of time if you plan on joining us, because they do sell out pretty quickly. And we have huge crowds. We stay up all night with our telescopes. You could get a chance to share the night sky with all of us, all through different telescopes. It's a great lot of fun. We support the Irving Nature Park locally too, and Rockwood Park in St. John through our regular outreach events open to the public. We offer mentoring to anybody who asks for it, and often set up for the public at local spots like St. Charles Beach. So we're going to talk about the night sky. That's our topic tonight. What about the night sky? About everything I can possibly bring up to you. So let's take a start, first of all, as we take a virtual journey from the center to the outskirts of the Milky Way. This this video here was captured by ESA, which is the European Space Agency, and we're going to walk ourselves through this now. So we're going to start out at the center of our Milky Way. We're 26,000 light years from the center. Our galaxy is 100,000 light years across. When we look out in space, we can see up to 75,000 light years across, but these are the stars that are orbiting the supermassive black hole at the center of our galaxy. That's called Sagittarius, in the area Sagittarius A. And we know that there's a black hole there. We can't see a black hole, of course, because it's black, but we can see stars over a 15-year period like this that do zoom around the black hole at the center. Now we're going to zoom our way out. Our galaxy has anywhere between 100 and 400 billion stars in it. It's a medium-sized galaxy. There are many that are much larger. We're going to see that as we move out as well. So we're going now about 10,000 light years out now through the Galactic Bulge, which is that large concentration of stars in the center there that make up about 50% of the total volume of the Milky Way. That is where the home is for about 100 billion suns. Now we move our way out to what we call the stellar disk. That's the disk that we see going across the sky. When we look up in our night sky, this is the view we get. Of course, we're inside one of the stellar arms. We're going to see that in a second here. There's also a large gaseous disk that surrounds us, and these large dots that we see around the outside there are called globular clusters. We have about 160 of those that we know of so far, and they orbit the Milky Way. Those are some of the oldest stars in the universe. Then there's a large dark matter halo, and then now we're going to zoom back in again, and we're going to look at our galaxy from above. Of course, we can't see it from above, but this is an animation, and these distances between these stars are actually calculated, and we're going to find out why here in a second. So we're going to zoom up above the Milky Way. We're going to find our location in the Milky Way. Of course, the spiral arms, we're barred spirals, what we believe anyway. There's the location of our sun, again, about 26,000 light years from the center. And this is also going to play in part when we look at our summertime sky against our wintertime sky a little bit later on. So this is something called the Hipparchus Survey. That's a telescope that just imaged that small part of the sky. But this Gaia telescope that's out there now can actually look at 30,000 light years of sky. And that's why we're getting a much better definition of what our Milky Way looks like. The Gaia spacecraft is actually something that's taking sections of the sky and imaging it over and over and over again, the full 360 degrees around us, which is giving us some great information. Okay, so from there, we're going to take a look at what we all see in school, right? This is, and again, this is a family-friendly show here, so if you want to bring on children and have a look at what we're offering here too, please, by all means. Our general solar system view is like this. I mean, we appreciate the 9 planets that are going around the solar system. We'll count Pluto at this point, but we can see that the ones that are on the inside, they go around a whole lot faster. That's Mercury going around very quickly there in about 88 days. Venus, of course, the next fastest, and then Earth, and then Mars. We can see the ones that are farther out there, Jupiter, Saturn, Uranus, Neptune. Jupiter takes a full 12 years to go around the sun. Saturn takes a full 30 years to go around the sun. Uranus is 84 years. So we're really getting out there when we're talking about some of them. But I like to look at our planets in this kind of format a little bit better. Excuse me. And this is placing things more in scale. So there's the 4 rocky worlds. They're in close. Then we have Jupiter, the gas giant. These are the gas giants, and the 2 bottom ones are called the ice giants, Uranus and Neptune. But there they are compared against the sun. So we could fit 1.3 million Earths inside our sun, and over 1,000 Jupiters would fit in the sun. So this is more of the scale of where things are. But we're going to take another look at it again in this format. And we're going to look at the solar system size and distance, because we were used to looking at magazines with the planets on them. They all look the same. They all look very, very close in the magazine page. But this gives us a little bit more of what the scale actually is. So here they are, all at the same size in distance, but not the scale though. So let's put them now in a spot where they would be the size to scale, but still not the distance to scale. So that's how we really appear. Now we're going to pan out from there to look at them in size and distance. And from here we'll see that we're just a tiny little speck there in that whole flue of things, but we can see how far away Saturn, Uranus, and Neptune really are when we're talking about distances from our sun to these other worlds that are out there, the gas giants. Of course, this is the more of the layout that we have. We see them from above in that picture there, but we're also going to look at the fact that if we did take all the worlds, though, we could actually put them between us and the moon. There is about 400,000 kilometers between us and the moon, rough an average distance, but all of the worlds would fit between us and the moon, still with about 8,000 kilometers to spare. So another thing that we want to look at is, of course, the rotation of the planets. So here's an illustration with Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all lined up. You can see that Jupiter spins around the fastest, the largest world, but still spins the fastest. Earth and Mars are pretty well close to each other. We're going to see that up at the very top. Venus rotates very, very slowly. Actually, Venus rotates every 243 days, but it only takes 238 days to go around the sun. So a day on Venus is like a year on Venus, kind of like a Monday for us, I guess. But Mercury rotates at every 58 days, so it's fairly slow too, and it takes 88 days to orbit the sun. We can see that, but Jupiter and Saturn, though, they're really the fastest ones. 9 hours and 55 minutes for Jupiter to rotate once, and Saturn only 10 hours and 33 minutes. So let's look at our rotation, not only our rotation, but also our tilt. And of course, our tilt is what gives us our seasons. We're tilted at a 23 and a half degree angle with respect to the plane of the planets. We're pretty similar to Mars. Mercury is almost straight up and down, and so is Venus. Jupiter is only 3 degrees tilted. Saturn is a full 26 degrees. Uranus is actually right on its side, about 97 degrees, and 28 degrees for Neptune. Venus is actually flipped upside down. We can see there it says 177 degrees, so it's actually flipped upside. How do we know it's flipped upside down? Because the North Pole is here and South is there. But it does take 243 days to rotate around the sun, so it's a very, very slow-moving world. If you were standing on it, you would only see one sunrise, one sunset with a year or so. Okay, I'm looking at questions here. Question for Chris: does star and planet size have any correlation as far as its location to the galactic core? Like, do stars and planets more near the core Does star and planet size have any correlation as far as its location to the galactic core? No, not at all. We take 250 million years to rotate once around the galaxy, our solar system completely, and we're very tiny in respect to the 400 billion other suns that are in there. And we're 26,000 light years from the core, so the core has no bearing on us at all. Hopefully that helps. Remember, please, folks, remember that I am just an amateur astronomer. I'm not an astrophysicist. I've never taken any courses in this at all. So it's just from when you've posed the question to me, I've tried to look up the answer. So I may be quoting a lot of misinformation, but I hope not. So from our seasons, of course, gives us our tilt. I mean, some of these slides too, you'll notice some of these slides that I've put in here are for beginners, and I presented a lot of these slides to middle school just this week. But we all know that it's all depending on our tilt, and our moon is what keeps our tilt. If it wasn't for the moon, we probably wouldn't have life on our world. We would be straight up and down, and there was no way that we'd be able to control our climate. So it's all depending on where our tilt is in respect to the sun, how sun rays affect us. So if we're in our summer solstice over here, the sun is almost directly overhead for us in the northern hemisphere. And right now, of course, we're closer to the sun actually in the wintertime. But the sun's rays are not directly overhead for us in the northern hemisphere. So that's why we have our winter. A little bit about the ecliptic itself. So when we see the planets lined up in the evening sky or in the morning sky, they tend to follow a line going up and down throughout the sky. And that line is called the ecliptic line, and there's a reason for that. Now, this is our orbital path around the sun. This is the heliocentric view. In other words, we're looking at the sun as being the center of the solar system, or the center of the objects here. But we're going to zoom back out here and look at what we call the geocentric view, which is going to show the Earth as being the center of our view here, as we see it. So here's our Earth, and we can see that the sun actually seems to rotate, pass through the constellations as it goes around us. As it goes around us? No, as we go around it each year. And that line that the sun and the moon and the planets take across the sky is known as the ecliptic. It's because of the angle of the Earth's rotation with respect to its orbital plane, the ecliptic is actually offset from the equator by 23.5 degrees. So that ecliptic line changes throughout the seasons as well. There are times when that ecliptic line is straight up and down. It all depends on where we are in relation to the sun as we go around the sun. Sometimes it's straight up and down in the summertime. Usually for us in the evening sky, our ecliptic is fairly low in the sky. So the planets kind of follow a low path across the sky. But in the daytime, of course, the sun is right overhead. So if we had views of any planets early morning sky or early evening sky, that ecliptic line might be almost straight up. So that's the ecliptic, and that's the line that we have to follow as we were looking for. If we follow along that line, that imaginary line that the sun and the moon and the planets take across the sky, if there's something along that line and it's a solid light instead of being a sparkling light or a twinkling light, then chances are it could be a planet. It's a good indicator. So from there, we're going to go through this, and this is a page I visit quite often, probably as much as I visit the program Stellarium online, and it's from heavensabove.com, and they provide an absolutely amazing amount of information on their page, and I congratulate them for that. There's ISS passes, there's the comets, what's happening with other constellation drawings, the whole bit. But this is the one I go to a lot when I'm trying to look at what's actually coming up in the sky in the next little while that I want to show others about. I would use this a lot for outreach. So I'm going to look at this planet summary. This is taken tonight at 5:20. And I've just plugged in, when I go to the page, up in the top right-hand corner, I plug in St. John as my location, and I bring it up. You can plug in your town as well. It'll populate for you. But I'm not going to look at all of these categories. The right ascension declination, the range is just the distance between us and the sun. How far? So we're 1 astronomical unit. So Mercury is 0.7. So 7/10 of the way we are to the sun is Mercury. Elongation from the sun, we're not going to talk about that. The brightness is really magnitude. So how bright objects are in the sky. We can see that Venus is a minus number. And the lower the number, actually, the higher, the brighter the object is. So the higher the magnitude. So Venus is at a minus 4.5, so that's fairly bright. The difference between a 1 and a 2 is 2.5 times exponential. So if something was a magnitude 2 and something else was magnitude 1, then the object that was magnitude 1 would be 2.5 times as bright as the object that is a magnitude 2. And then you would go farther. If something was a magnitude 0 against the magnitude 2, then it would be 2.5 times 2.5 times, so 6.25 times as bright as the object was at magnitude 2. So the lower the number here, the brighter the object. And we can see now that Venus, out of all the planets, at least, Venus is the brightest object in the sky. Second up is Jupiter at minus 1.9, so it's 6 times less bright than Venus is right now, roughly 6 times. So that's a brightness category. We're not going to look at equatorial, these ones, the constellation that it sits in. That can be helpful. Mercury, Venus, and Mars are now in the morning sky. That's where Sagittarius is right now. Sagittarius will swing back to our evening sky as the summertime approaches. We can see Jupiter sitting in Aquarius, Saturn's in Capricornus, and away we go. These ones here are the more important ones. The rise and the set times. So we can see that Mercury rises now at 6:54. Venus rises at 5:43. Mars rises at 5:50. So the first thing up after this, before the sun rises, would be Venus, and then Mars, and then Mercury. And we're going to see that a little bit later. Jupiter's up at 9 o'clock, so we're not going to catch that one yet. But we see it in our evening sky. See how it sets at 1941. The sun is already set by that time. We still see Jupiter in our evening sky. So these two lines here are very important. And if you want to find out what planets are up that particular night, you can go here too and change the date. Select it ahead for a couple of months if you like, and the rise and set times will change. I'm not going to look at altitude or azimuth either. Inferior conjunction is something that we're going to look at here in a second or two. Inferior conjunction means that those worlds are between us and the sun. And there's only two worlds that can become between us and the sun, and that's Mercury and Venus. All of the other worlds would be at superior conjunction. They're farther out. They would be on the other side of the sun from us. So only two can be on inferior conjunction. The next inferior conjunction of Mercury is May 21st of 2022. So that means it's going to be between us and the sun on May the 21st. Venus' next inferior conjunction is August the 13th. Now, if we go down this line, we look at Saturn here. Saturn, its next superior conjunction right here is February the 4th. So that means Saturn is going to be on the opposite side of the sun on February the 4th. Jupiter, it'll be on the opposite side of the sun on March the 5th. So we can see Jupiter in our evening sky now. It's getting lower and lower and lower, and that's because it's going to fall behind the sun from our point of view. Maximum eastern and western elongation, that just means how far east in the sky that planet can be, or how far west in the sky that planet can be. How far east it can be in the evening sky, or how far west it can be in the morning sky. And usually when it's the farthest east or the farthest west, that's when it's the best viewing. Perihelion means the closest approach to us, and aphelion means its farthest approach away. So this chart we're going to refer to a little bit farther down here. So let's keep going. I got a lot here to present, and I know there's a lot of material that I'm presenting here all at once, but you can always play this back as well. This will be recorded, of course. It'll be up on Facebook and YouTube, both. So if you want to go back and review it and slow it down, pause it a bit, please do. Okay, so when we talked about conjunctions, first of all, we want to look at what's an inferior planet and what's a superior planet. Well, the inferior planets would be the ones that are between us and the sun. So Mercury and Venus are between us and the sun. So those are the only two that can go to inferior conjunction, which means they would go between us and the sun. The superior planets, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, of course, are the only worlds they can't get between us and the sun. They're farther out from us. So those are the worlds, if we were on this side of the sun, they would be at superior conjunction. So when you hear something that says it's at inferior conjunction, you'll know that it's between us and the sun. If they say it's a superior conjunction, it's on the opposite side of the sun from us. Okay, let's keep going. Boggled you enough now, let's keep going. So we've got the sun in the center here, and we have this we called inferior conjunction. That would be Mercury or Venus. But they can also be the farthest west or the farthest east we can see in the sky. And this is where they would be in relation to us if we were to look down on top of the solar system, which we can't do, But if we could look down on top of the solar system, this is what we would mean. So when, say, Mercury is farthest east in the sky, that would mean that the sun has set and Mercury has moved as far east in the sky as it possibly can. The same thing with the western sky. That would mean the sun has risen and Mercury is as far west in the sky as it can be. So inferior conjunction, the inferior planets are between us and the sun. Superior conjunction is when those planets are on the opposite side of the sun from us. So this could be Jupiter, that could be Saturn. And when a planet is at opposition to us, that means the sun, the Earth, and that planet are lined up. The two inferior worlds can't go at opposition, they can only go at conjunction. The outside worlds can go at opposition. So we're in the middle between the sun and that planet. When we're between, if that happens to be Jupiter, and we're between the sun and Jupiter, then that means that Jupiter would be up all night long, and when the sun sets, Jupiter would rise, and when the sun rises, Jupiter would set. So when a planet is at opposition, that's when it's at its best viewing, because when it passes the meridian, or that halfway point in the sky, that's when it has the best viewing. The higher the objects are in the sky, especially planets, because they reflect sunlight back at us, the less atmosphere you have to look through to see a clear view of it. So you want to see a planet at opposition when you get the best viewing. Okay, back to our planetary view again. So same idea. We'll look at opposition here. Here's opposition lines. So Mars at opposition. Mars is going to be at opposition on December the 8th of this year, which means it'll be the Sun, Earth, and Mars all lined up. That means the best viewing for Mars is going to be in December of this year. Jupiter's best viewing will be in late September of this year. September the 26th is when it's at opposition. So it's a few weeks on either side of that's best viewing. Saturn is going to be at August the 14th. And that's because we go around the sun every year, and it takes Jupiter 12 years to go around the sun. So of course, every year we catch up to Jupiter. We can see that Mars, though, its last opposition was in 2020. So it takes us 2 years to catch up to Mars, a little bit more than 2 years, because Mars is just a bit farther out from the sun than we are. So it does take us 2 years to catch up to Mars. But we catch up to these other worlds every year. So best viewing for Mars is going to be in December. Best viewing for Jupiter is going to be in late September. Best viewing for Saturn is going to be in mid-August. So far, so good. Hey, sis, how you doing? Okay, we'll keep going. There's another one I'm going to show you. So this is another view. When you go to heavensabove.com, you can click on something called Solar System Chart. So this is our solar system looking down from above, and we're looking at where all the planets are located at the moment. And this is a really important one, because if you can understand this one, you'll understand why things are in the sky when they are. So we have Earth, Venus, and Mercury. Mercury, Venus, Earth right there, and Mars. That's that small little square there in the center, because these ones are so far away we have to put the other four in this little square. Then we have Jupiter, Saturn, Uranus, Neptune, and Pluto. But we need to look at it like this, because if we look down on top of the solar system, everything is rotating counterclockwise. So if we're flying above the solar system looking down, everything would be rotating counterclockwise, including the Earth, as we would be rotating counterclockwise here to give us our daytime. So this is going to come important as we go to the next few slides, because I'm going to take this slide here and I'm going to reveal how we find these objects in the sky using this chart. And that's going to come up a little bit later. But first of all, I think we're going to get into the solar system itself. So we're going to take a look at our sun first, of course. Our sun is a 4.5 billion-year-old star. It's a hot glowing ball of hydrogen and helium at the center of our solar system. Now the sun is about 150 million kilometers away from us. And without its energy, of course, life would not exist on our world at all. The sun converts 600 million tons of hydrogen into 595 million tons of helium every single second. So it's like billions of nuclear bombs going off every second. It's been doing that now for 4.5 billion years. The only reason that the sun doesn't blow itself apart is because it has such a massive gravity that wants to crush the sun at the same time. So it's in equilibrium there. Something that wants to blow it apart and something that wants to crush it. Keeps it in equilibrium for the last 4.5 billion years. These are sunspots that are going around. Each of these are much larger than the Earth. Our sun goes through an 11-year cycle where we have a very slow part of our cycle when there are very few sunspots happening, and then a very active part of our cycle when there's many sunspots on the sun. We're moving from our minimum part of the cycle now into our maximum. We're just coming up out of the minimum to the maximum. That's the actual planet Venus passing in front of the sun during a transit, what we call a transit, when those worlds do pass in front of our sun. Because it's an inferior planet, there are times when it is correctly lined up that we will get to see Mercury pass in front of the sun like that. Now, the sun is the largest object in our solar system. The sun's volume would need 1.3 million Earths to fit inside it. Its gravity holds the whole solar system together. It keeps everything from the biggest planets to the smallest bits of debris in orbit around it. And the hottest part of the sun in its core is about 15 million degrees Celsius. And what we call the surface of the sun, or the photosphere, runs about 5,500 degrees Celsius. Well, sunspots appear black like that because they're about 5,000 degrees Celsius. So they're a little bit cooler than the surface of the sun, the rest of the sun, so they appear black. But if we took those sunspots and put them out in the space, they'd be as bright as a full moon. So the sun doesn't really have a solid surface because it's just a big ball of plasma. And because it's a big ball of plasma, it does rotate at many different speeds. It's not a solid ball like us that we rotate at one uniform speed. It rotates at many different speeds. And when it does that, it has huge magnetic lines, of course. So those magnetic lines get twisted a lot. And as they do, those lines twist around and they'll open up and sunspots will appear on the surface. And when that happens, sometimes these large loops of plasma that I showed here just a second ago will form. And these large loops will form and they'll short circuit. The two edges will actually touch back together again. And when they do, they produce a solar flare. Now, if the solar flare is large enough, it becomes what we call a CME, or coronal mass ejection, where billions of tons of material right there are being released into space. If we happen to be in the path of that material, then it excites our upper atmosphere, and of course our magnetic lines protect us from the biggest part of the damage, but where it's weakest at our poles, these electrically charged atoms come into our poles and they excite other atoms in our atmosphere like nitrogen and carbon and things, or nitrogen and oxygen and things, and that's what gives us our northern lights. So that's why when the sun is active, there's more of an opportunity to catch aurora because there are more chances for eruptions on the surface of the sun. Now, the sun releases more energy in 1 second than mankind has consumed since we've been here. The funny thing about the sun too is that the sun has this photosphere, but also as we step farther away from this, we said that the surface of the sun is 5,000 degrees, but the farther away we step from the sun till we get out to a distance here, it's up to 10 million degrees. And we're not quite sure yet why it's hotter when we step away from the sun out to a distance. When you sit by a campfire and you move away from the campfire, of course, you feel colder because you're moving away from that source of heat. But in the sun's case, it's different. So this 10 or 15 million degrees that we see at the surface down here is about 10 million degrees here. And this is the part that we can only see the corona when we have an eclipse. So we're not exactly sure why that's happening, but we do have a spacecraft that has touched the sun recently called the Parker Solar Probe, and it is investigating this actual phenomena. So we hope to get more information about that very soon. Carry on. So here's a sunspot in relation to the size of the Earth. This is just an average size sunspot, nothing spectacular, but I'm going to turn off the heat here behind me. There, don't need the fireplace on. So nothing spectacular about that special sunspot there, but that's roughly the size of most sunspots on the sun. And there's another example of some loops of plasma compared in relation to the scale of the Earth. So 1.3 million Earths would fit inside the sun. There's another grouping of sunspots through my telescope, or one of my telescopes. So they look pretty nice through that type of an image. That's just a white light filter that's set, a solar filter that's put on the front of your telescope, always on the front of your telescope, never on the back where your eyepiece is. And that will filter out 99.999% of all the damaging light rays that would bother your eyeball when you're looking through the telescope. But that's just a simple white light filter. An H alpha telescope will change that to view not just sunspots, but also the plasma loops that are up around the edges here, the prominence as we call them. So here's the surface of the sun. This is from a new telescope that came out in 2019, and it actually shows us action happening on the surface of the sun. This is amazing. Each one of these pieces that we see here are at least the size of Texas, at least. So we can see that there's a lot of bubbling action happening on the surface. So the sun is very active, always active, and that's because the fact, again, that's a huge ball of plasma. There's no solid surface on the sun, and it does rotate at many different speeds. So that's what causes all these magnetic lines of force to twist and stuff, and that's what causes a lot of the action. Of course, it's 15 million degrees down at the center. That energy is trying to reach the surface of the sun. It takes millions of years for those photons to reach the surface of the sun, but only 8.5 minutes to reach us from the sun. So moving forward now, I want to take a look at our sky and what we would see for planets in our sky. We'll start there, I guess. But I want to show you what you can see with binoculars. And I mean, programs like Stellarium, if you go to stellarium.org, you download that program. I use that one a lot. There are a lot of apps out there, of course, Starwalk and many others that work very well. This one I've used from the beginning because I find that I can find more features inside it, especially if I'm using it from my desktop or laptop. So I'm going to show you basically how we find these targets in the sky just for the next little bit to get you used to looking up and looking for planets in our night sky. So we're going to start, first of all, we're going to look at the planets as we move our way out the solar system. So we'll take a look at Mercury, first of all, the smallest planet in our solar system, and it's the one nearest the sun, of course. Mercury is only slightly larger than Earth's moon. From the surface of Mercury, the sun would actually appear more than 3 times as large as it does if you viewed it from Earth. And sunlight would be as much as 7 times brighter than it is here on Earth. Now, despite its proximity to the sun, Mercury is not the hottest planet in our solar system. That title actually belongs to Venus, thanks to Venus's dense atmosphere. So Mercury is a rocky planet, also known as a terrestrial planet. The 4 inner worlds are. Mercury has a solid cratered surface, much like the Earth's moon. And the reason why we believe that Mercury is so covered with craters, if I didn't tell you that was Mercury, you might even think that was the moon. And the reason why it has so many craters is because Mercury sits fairly close to the sun compared to us. And it's in the path of all of these asteroids and comets that happen to come in and be drawn in by the huge gravity of the sun. So little Mercury is in its way sometimes, and it unfortunately has had a lot of impacts. Now there's very thin atmosphere on Mercury, not enough that we could breathe at all. It's unlikely that life, as we know, could survive on Mercury due to any the solar radiation alone. The solar wind has stripped away its atmosphere long ago. But solar radiation would be a real concern, and extreme temperatures on Mercury as well, because Mercury doesn't have an atmosphere. It can't modify its temperatures. And because it is the closest planet to the sun, it does orbit the fastest of all the planets, just 88 days for Mercury to go around the sun. So from there, let's go back to our, I want to have a look at this first of all. So we have something called the transits of Mercury, and we have transits of Venus as well. About 13 times a century, our Earth, the Sun, and Mercury line up. You can see that Mercury's tilt is a little bit out of ours, about 11 degrees or so tilted, or 5 degrees apparently, tilted with respect to the plane of the planets. So here it is here. That's Mercury's orbit compared to our orbit. So there's only certain times when Earth, Mercury, and the Sun will line up, and that happens to be when Mercury passes these things here we call nodes. So either Mercury is moving from the lower part of its plane above our plane, or it's moving below our plane. And if it happens to do it over here and we happen to be here, well, we're not going to have an opportunity to see a transit. If it happens over here, of course, we can't see it either because Mercury is higher than the sun. But at these particular points right there, that happens 13 times a century. We're able to watch Mercury pass in front of the sun. From our point of view here on Earth, very tiny, a lot smaller than what we saw for Venus there, but it does happen. I think the next one is in 2032, I believe, the next opportunity for us to see the transit of Mercury. The last time we missed it because of a cloudy day, which happens on sometimes with events, more often than not. Okay, so let's take a look back at our chart again, a solar system chart. Here we are, we're all rotating counterclockwise. The Earth is rotating counterclockwise. So concentrate on Earth in here. And this is you out here standing on the Earth. So let's rotate counterclockwise. As we rotate counterclockwise, what's going to come up before we see the sun? Okay, so as we turn around this way, hey, there's Venus, there's Mercury, and there's Mars. So which one will we see first? Well, Mars we'll see first because it's lined up better. Then we'll see Venus, and then we'll see little Mercury, and then we'll see the sun. So follow that. And again, now that's a ball rotating counterclockwise. We're standing here. As we turn around, we see Mars first, we see Venus next, then Mercury, and then if we keep turning, we'll see the sun rise. Okay? Keep that in your head, and we'll go to this picture because here's where we are. This is our morning sky. So because of the placement of the planets where we're seeing them right there, Mars came up first because it's the farthest west. Venus came up next, and Mercury was then, and then the sunrise after that. So here's your view on January 31st, looking southeast at 7 o'clock in the morning. Now you might want to be 6:45 because you're going to have a fairly bright sun there, so you'll get to see Venus for sure, probably Mars, maybe Mercury, really a little tough. You might want to start a little bit earlier for Mercury. But we can see that Mars came up first, Venus, and then Mercury. So that's the plan. Looking at that solar system from above, looking down on it, if the light bulb comes on, you're going to see how easy this is. So let's go from there now out to Venus. What about Venus? Well, Venus, of course, second planet from the Sun, Earth's closest planetary neighbor. I'm going to try to get this to start again. It's one of the four inner worlds, of course, often referred to as Earth's twin because it's similar in size and density as the Earth. But that's where the similarity actually stops. There are actually very radical differences between the two worlds. Venus has a very thick, toxic atmosphere of carbon dioxide, and it's shrouded in a thick yellowish cloud of sulfuric acid that traps heat, causing a runaway greenhouse effect. So Venus, we'll see here shortly, is surrounded by carbon dioxide. That's what gives it such its reflective properties. That's why it's so bright in our sky, in our morning sky. It's because it's reflecting so much sunlight back into space. About 97% of the light that hits Venus actually gets reflected back. But a lot of it gets trapped inside underneath the clouds, and it can't get back out. It's like having a big blanket around the planet. So it does rain sulfuric acid on Venus. The sulfuric acid, as far as we know, doesn't reach the surface, but it does cause the planet to heat up. The planet runs about 457 degrees Celsius, hot enough to melt lead. The surface is a very rusty color, and it's peppered with intensely crunched mountains and thousands of large volcanoes. Now, the reason why the mountains are crunched is because there's such a pressure pushing down on Venus from the clouds. And actually, if you stood on Venus, on the surface of Venus, it would be 92 times the pressure that we experience here on Earth. It would be like you standing on the bottom of the Atlantic Ocean. So it would be a very crushing experience. Whether or not you'd actually be able to stand up would be very tough. Another big difference from Earth, too, of course, is Venus rotates on its axis backwards compared to most of the other planets in the solar system. And it does rotate every 243 days, rotates around the sun every 238 days, so a day on Venus is actually longer than a year on Venus. Some cool little facts to tell your kids. Okay, and this is one of the few photos that was ever taken from the surface of Venus. The Russians did send a number of spacecraft to Venus. Veneras, they were in the late 70s, early 70s to late 70s, and this is one of the few photos that was actually taken from the surface of Venus. I believe the camera died shortly after it took this one photo. So, very hellish world, not something that we want to stay around for sure. But Venus is a beautiful object. We all really like it. It's our morning star now, so here we are again looking down on our solar system. Same thing, we're looking counterclockwise as we were before. Everything's rotating counterclockwise. Here's Earth. We're rotating counterclockwise. As we rotate again, the first thing we see is Mars, the next thing we see is Venus, and the third thing we see is Mercury before we see the sun. So let's go back to our view again. Here we are again in the morning sky. So Mars, brilliant Venus, the morning star, very, very bright, the brightest object you're going to see in the morning sky. and then dimmer Mercury down here to the east. Okay, next up, of course, Earth. The only world that we know of anywhere that supports life, 70% covered with oceans, has a great tilt, has been kept that way by our moon, and it's taken us a long time to form life here on our world, about 4.5 billion years old. So not much we can say about that is that, but the fact that it's very unique and the only place we know where life does exist so far. We're still looking for places other than our world. Our atmosphere, of course, protects us from incoming meteoroids, most of them which burn up in our atmosphere on the way through. Our magnetic field protects us from the solar wind, so we're able to have an atmosphere. It's not swashed off into space. So there's a lot of things that have allowed us to have life here on our world. If we stepped out a little farther than that, we'd get to our moon. So these are images from the Lunar Reconnaissance Orbiter, which is a spacecraft that's been orbiting the moon now for 11 years. It's owned by NASA, and it does take high definition photos of the moon. We've learned a whole lot about the moon from this simple spacecraft, and it's been there, and it's solid. The spacecraft that they're coming out with lately are just getting amazing with what they're being able to do with them. But that's a full view of the moon, and we only see this side of the moon because the moon is tidally locked with us, or it's what we call synchronous rotation. So the moon takes the same length of time to rotate once on its own axis as it does to go around us once. So that's why we always see this side. We call this side the near side. The other side is not the dark side, it's actually the far side. The moon gets the same amount of sunlight, front and back, as the way it works through its phases. We're going to see that in a second here. How did the moon form? Well, there are several theories about how the moon formed, but we're going to take a look at what the leading theory is now. And so we think that back in the early days of the solar system, we're looking at about 4.5 billion years ago now, when our Earth was just forming. You take a snowball and you roll it in the snow, and how do you make a snowman? Well, you take a snowball and you roll it, and the more you roll it, the bigger the snowball gets. Same thing with a planet. When you start it with smaller rocks, that gravity pulls in larger rocks, and that gets more gravity, so it pulls in more rocks, and then you end up with a ball. But here comes an object about the size of Mars that we call Theia, and we believe that it crashed into our early Earth and almost destroyed us. There would have been a larger number of planets in our solar system in the beginning than there are now, of course. The bigger ones won out, but here comes that rock melding everything together. The material from that planet or planetoid and our planet mixed together, homogenized together. Some material got cast into space, and eventually it coalesced to form our moon over 1 million years or so. So our moon was molten, and so was our planet, and made of the same material. And we believe this because of the material that we brought back from the moon, the 805 pounds that we brought back from the Apollo missions. In fact, when we're looking at the moon in this state here, the moon would have been about 18 times closer to us at this time than it would be today. So you can imagine how large the moon would have appeared in our sky, being at 18 times closer. The Apollo landing sites, of course, from 1969 to 1972, we took 12 humans to the moon. 12 humans walked on the surface of the moon, I should say. There was 1821, I guess, that actually went to the moon. Apollo 13 didn't land, of course, but there's Neil Armstrong's first footprint in the Sea of Tranquility. There's Apollo 16. One of the astronauts from Apollo 16 actually took a picture of his family and left it on the moon. We've got Apollo 12 here with the Surveyor spacecraft. Apollo 12 was trying to land as close as they could to this Surveyor spacecraft, and they did get there. There's their lander back here in the background. Apollo 15, Apollo 17 with Eugene Cernan standing beside Harrison Smith. The first geologist that actually went to the moon was on the last mission to the moon. We didn't take a geologist before that. These guys were all Navy pilots or air pilots, Air Force. And there were no women on the moon. Why we didn't take women on the moon? Different times. You had to be a man to be a test pilot, and you had to be a test pilot to be an astronaut. So that ruled them out. But if it wasn't for women, we couldn't have gotten to the moon. You may have seen some movies on that, on what they did in the background to calculate all this information. We are going to take the first woman to the moon in 2024 when we go back with the Artemis mission. Very excited for that to happen myself. Looking forward to us exploring the moon once more. We should never have left the moon, in my opinion. We went to low Earth orbit, and that was because the race to the moon was over. We had beaten the Russians to the moon. That's what it was all about. And you can't say we didn't go to the moon because they would be the first to call it out. And here are some photos for proof or evidence, if we want to call it that. This is from the Lunar Reconnaissance Orbiter that orbits the moon, as I mentioned, and these are the 6 Apollo sites that were visited by the Apollo spacecraft. There's the Lunar Module from Apollo 11. This is Neil Armstrong's footprints leading out to Gale Crater and back again. Here's some of the experiments that were left behind. There's the camera, where the camera was sitting over here. Here's Apollo 14 site. There's the lunar rover. We actually took some electric vehicles to the moon. The Surveyor spacecraft that I mentioned earlier, there's the Apollo Intrepid stage that landed, and there's their walk down to Surveyor to pick up some information, data that they brought back actually. There's a second LRV over here, Apollo 15, and here's the last one here, final parking spot of Apollo 17. Again, this is one of the few pictures that we actually have of the far side of the moon, taken in respect with the size of Earth compared to the moon from that vantage point from one of the Chinese landers. And here's some of the footage that we had captured while we were at the moon. I believe this is from Apollo 15. Watch the dirt here. This is the one I like to show this because I like to show that we're on the moon. If you watch the dirt spinning up from the tires there, you can see that it goes straight up and straight down. It doesn't blow around. It's only straight up and straight down. We'll get a better look as it comes around the corner here. You can only do that on the moon. You can only do that in a vacuum. So could you have a vacuum that large for it to happen? You know, it would cost more to fake the moon landings than it did to go to the moon. So we have to understand that part. And you're only 1/6 of the gravity that you are here on the planet as well, so you can see how easily it would be to bounce around on the moon. Can't see stars? No, you can't see stars. The reason why you can't see stars is because we're focused on the moon itself. The moon is very bright. It's actually not that bright when you're there on the surface. It looks more like worn asphalt. Not that I've been there, but it looks more like worn asphalt. But when you set your exposure to reveal the moon's surface, then you can't see the stars in the sky. If you had set them to see the stars in the sky, then the moon would be completely blown out. And if you've taken any photos at all of the night sky, you would understand that part. It's not overexposed. This is underexposed to reveal the surface of the moon. So we drove around on the moon because we want to get farther away to get more samples to bring back. 805 pounds of moon rocks we brought back over the 6 missions. Why do we see phases of them? How are we doing anyway, folks? I think we're into 8:53, so we're into almost an hour already. But if everybody's okay, we'll continue on. No other questions. I've been watching your comments, but I haven't seen any questions. Maybe everybody's just kind of sitting looking at the screen. That's good too. So anyway, why do we have phases? Well, there's a particular reason why we do have phases. This is it. So this is from NASA, and it's an animation, of course, showing us the position of the Earth relative to the moon, and why we see the view on the side here on the right is the view that we get from Earth when we're looking at the moon. We can see that the reason why we don't see the whole moon now is because the sun is shining on the opposite side of the moon, that dark side of the moon that we talk about. We can also see that the moon rotates very slowly. Every 28 days, it takes for it to rotate once on its own axis, and that's why we always see this same side of the moon. No matter what we're looking at from our point on Earth, we're always seeing this same side. Here we are coming around to the full moon part of the cycle. So that's why we see the moon as we do. When the moon is full, it's behind us in relation to the sun, and we see it fully lit from our point of view. Of course, when we're looking out at planets and the other parts of the solar system, that's what we see as well. We can see Venus and Mercury as crescent phases because they're inferior. They're closer to the sun than we are, so we will see those in phases. Farther out now. Okay, so let's talk a little bit about supermoons. Hey, we've all heard about the term supermoon, and that was a term that was brought up in the 70s, or early 80s, I guess. And it was just a suggested term, but it stuck because people wanted to have a term that they could kind of pick out. So here we are with our moon at perigee, the closest approach, and apogee, the farthest away approach of the moon. Much difference? Not a whole lot. There they are on the right-hand side with a perigean moon and an apogee moon. So this is a supermoon, and this is what we call a micromoon, so the farthest away moon that we would have. The difference to us, yeah, you know, if you stood there and knew exactly what size the moon was last month, you might be able to tell. But it's more to do with this. So this is what we call the moon illusion. And the moon appears large in our sky at times, and other times it appears small. Is it actually closer on a supermoon? Yes, it is. But we're comparing it. So look at this. Look at this view, for instance. Okay. So the two tracks are shown here, where the moons are located, and the moons are actually the same size here. The reason why we see it larger at the top is because we're comparing against something at the distance. Our eyeballs are traveling out to the distance there, and we're comparing against mountains and things that we see at the edge. So we say, hey, mountains are farther away. They're big. The moon must be bigger. But when we're looking at the moon closer up, we're looking at the moon as if it was up in the sky. I'll show you that in the next slide, called the Ebbinghaus Solution. So here we are. So let's picture this as being the same thing as what we just saw. Which of these inner circles is larger? They're both actually the same size. It's our brain playing a trick on us. Okay, so when we see the moon like this, we're picturing this as being the scenery around the horizon, the buildings, the mountains, and that kind of thing. And the moon looks very big next to those because our eye sees that as the moon's being farther, the mountains are farther away, so they must be larger, so the moon must be larger than that. If we picture this as being the moon in our open sky, this would be our sky all around it. It does appear small. Go out, and next time we have a supermoon, hold your thumb up to the moon, and you'll cover the moon with your thumb when it's at the horizon. No matter how big it looks, you'll cover it with your thumb. Wait till the moon gets up higher and place your thumb out again. It'll be the same size. It's because we don't have anything. When the moon is up higher, we don't have anything to compare it against. When it's lower, we have buildings and horizons and mountains and things like that to compare it against. But when the moon is up higher, there is nothing around it to compare it against, so our brain sees it as smaller. Another way to do it is to just make a small fist, poke a hole through the center of your fist, and when the moon is large at the horizon, look at just the moon through your fist, and you'll see that the moon has actually shrunk just by putting your fist up and looking through the center, because your brain isn't looking at the rest of the objects, just the moon by itself. So that's something called the moon illusion, and that plays more of a factor in the supermoon view than anything else. So if we went from the moon, I don't know if we had something else here or not. I think we did. Oh yeah, so now we're going to talk about asteroids. So between Mars and Jupiter, we're talking about asteroid belt. I should have moved out a little farther before I got that one. There's a large asteroid belt. This is the view of the known asteroids up to, I believe, 2018 or 2019. So you can see the amount of asteroids that we found here. I want to take that back a little bit from the start. So this is when we were just beginning to find asteroids. There we are. There's Mercury, Venus, Earth. That's us out here in that whitish bluish circle. There's Mars out there. So between us and Mars, there's a large number of asteroids. And we get better and better with our telescopes. That's what happened. Our telescopes get larger. We were able to look out at the sky better. There are other telescopes like TESS and other telescopes that have been orbiting the planet that are actually finding asteroids as well. So we can see that this is back in 2009, how many we saw. And as we move ahead in time, there's 2018. It's 9 years later. And as we zoom in here to the end, this is all the known asteroids in 2018. So if we want to look at that little circle in there, there's us. And look at the number of asteroids that are passing in and out of our path as we go around the sun. So a huge number. Are they directly in our path? No. A lot of them, what we call near-Earth asteroids, are. Those are the ones that are the dangerous ones that are usually over a kilometer in size, or actually I think over 100 meters in size, they're calling them now, that could be potentially damaging or to potentially hazardous asteroids. They call them PHAs, and they could be hazardous to us. But there's nothing in the next 100 years, at least, that we looked at that are going to be of any detriment to us. Of course, we're finding new ones all the time, and sometimes they go by us first before we get to see them. We don't. They're in our shadow, and all of a sudden they pass across the sky, and we see them as they're leaving, and they're a lot closer than what we thought. But we're getting better and better at finding them. So we're actually getting ready to send a spacecraft out to actually kind of nudge one of the asteroids to see if there's something that we can do. If we can nudge it, if we know that there's one on a path to Earth, on a collision course to us, could we nudge it way out here, just a small amount, and set it off course so that it avoids us completely? That's what we're going to be looking at very soon. I'm not sure what the name of the mission is, but I got to look it up. But there's just so much happening, I can't keep up with all of it. But I know there is a mission set for that soon. So let's go from there to, I guess we're going to go to Mars next. Yeah, we're going to go to Mars next. Let's have a look. Okay, so Mars. Of course, fascinating world now. It's the only other world that is completely inhabited by robots that we know of. There you go. So Mars is the fourth planet from the sun, a dusty, cold desert world with a very thin atmosphere. Mars also has a dynamic planet with the seasons, polar ice caps, canyons, extinct volcanoes, and evidence that there was even more active in the past. We're going to see rotate here into a view of the largest volcano in the solar system, which is Olympus Mons. And it should be coming around here soon. There's the canyon I talked about. There's Olympus Mons coming right up here. So if you actually were standing on Olympus Mons and walking away from it, you wouldn't believe you're actually walking on it's so large that the hill is a very, very shallow grade, about 7% grade. So you would actually be just thinking you're walking down a hill for a long distance. Mars is one of the most explored bodies in the solar system. It's the only planet where we've sent rovers to roam around the alien landscape, of course. NASA currently has 2 rovers on the surface, a Curiosity and Perseverance, 2 that are active at the moment, 1 lander called InSight, and a helicopter, Ingenuity, which took its last flight, I believe, last week, exploring the surface of Mars. Now, a day on Mars takes a little over 24 hours. Mars makes a complete orbit around the sun every 687 Earth days. Mars has a very thin atmosphere made mostly of carbon dioxide, and it has 2 moons named Phobos and Deimos, Fear and Terror. They're actually just captured asteroids. They're not shaped like a moon. At this time, Mars' surface cannot support life as we know it, but could it have done it long ago? So we're now there on Mars, and we're looking around for signs of microbial life or some other form of life. Could there have been life at one time on Mars? Was Mars covered with oceans at one time? Yes, we believe it was. That's what caused these canyons. We can see riverbeds on Mars, rocks that are polished, almost like they were sitting at the bottom of a stream. So we know that water did exist on Mars, and we know that water's needed to create life or to support life. So could there have been life at one time on Mars? It's a fascinating concept. And the whole push here is that, look, if we find life on Earth and we have life on Earth, if we could find that it did exist on Mars at one time, then that's 2 out of 8, we'll say, possibilities of life in one solar system. Well, if you take that by 400 billion stars, and we know now that there's at least 1 planet around every star that we've looked at, that's 400 billion planets in our galaxy. So that could be the odds of 100 billion worlds out there with something, just in our galaxy alone. We're not talking about life as DART. Thank you very much, Joey. Double asteroid redirection test. That's the one that's going to go out and hit the asteroid or tap the asteroid, I guess. But if we can find life in 2 worlds, or that life did exist on Mars at one time, then that brings our possibilities up higher for life out there somewhere in the solar system. Do I believe that there's life out there in the solar system? I can't believe that there isn't. We're talking about 400 billion stars in our galaxy among 2 trillion galaxies. How many planets is that? We found systems here with 7 and 8 planets in them just recently. So that's the big push for Mars. I mean, it's going to take us 8 months to get to Mars. It takes us 2 years to stay on Mars because we It takes us 2 years to catch up to Mars, and we don't launch when we catch up to Mars. We launch before we catch to Mars, and then we head to Mars, and then on our way back, we pass Mars and let Mars launch and catch up to us. So we've got to do a whole lot of things before we ever get to Mars. First of all, we got to go to the moon. We got to learn what it's like to live on in an environment where we don't have any type of protection. Are we going to build a city on Mars? Elon Musk says so. Yeah, I think we're a ways away from doing that. But we first of all we have to get more robots there to build what we need to have to survive on Mars. We need vegetation. We need some place to survive inside of. We need to send a rocket there, and we need to produce rocket fuel. But we do know that underneath the surface of Mars, there is lots of water. There actually believe there's more water under the surface of Mars than there is in all the oceans on the Earth. It's just frozen underneath the surface. And that's because Mars could never hold onto its atmosphere. Because Mars is about quarter of the gravity of Earth, it supported an atmosphere at one time, we believe, and it rained on Mars and the whole bit. And as that atmosphere would escape off into space because of the gravity that couldn't hold that atmosphere, volcanoes would replace that over time. But then eventually, once the volcanoes died, Mars was doomed. So more water would evaporate into the atmosphere and would escape away from Mars altogether, and then Mars became this climate that it is today. So, of course, there are dust storms on Mars too that flare up. Mars seems like an active world. It does have seasons. At the equator on a summer day on Mars, it could be 20 degrees C. At night, it's over minus 100, so it's not quite as comfortable. But there are huge dust storms that take place on Mars as well that engulf the whole world. And there are times when we don't see any features at all like this on Mars. The whole world would be covered with dust. That happened just a short while ago. A couple of years ago, I believe we had a huge dust storm on Mars. So it's still a very fascinating world for us to discover. Now, go from there to back to our drawing again. Here we are. So back to our counterclockwise view of the solar system from above. Here's our counterclockwise view of the inner planets from above. Here's our planet, counterclockwise again, so we're going to do it again. Earth, we're rotating counterclockwise. The first thing we see, Mars. The second thing we see, Venus. The third thing we see is Mercury, and then the sun pops up. So back to our drawing. Here we are again. Mars, Venus, and Mercury, and that's why we see them in our morning sky. It's just that easy. Once you get a feel of what that drawing is above your head as you're looking down on it. Okay. Another thing about Mars, Mars is coming up to opposition this year. We did talk about that December the 8th of 2022. So that would be when we have the Sun, Earth, and Mars all lined up. So as the sun sets, Mars would rise. As the sun rises, Mars would set. So it's going to be up in our sky all evening long, the best viewing. And we want to be really at a time when Earth is farthest away from the sun and Mars is at its closest approach to the sun. This distance here is important. That's when Mars appears its largest in our sky. It's not going to happen this year. We'll be close to it, but won't be quite on the button. It happened a few years ago when Mars was not only at opposition, but it was at its closest approach to us at the same time. So we had a chance to see better features on Mars. Will Mars ever be as large as the moon in the sky like it was in those ads? No, it'll never happen that way. If Mars ever gets as big as the moon in the sky, you want to run and find a cave somewhere. We'll step out from Mars now and go to Jupiter. Jupiter, of course, is the next world out past Mars. We're getting into the gas giants now. Why are they gas giants? Possibly because when the solar system formed, we were a big ball of gas at the center, and material was pushed out by the solar wind. The material that was left over, the gases were lighter, of course. They moved out farther out. The rocky worlds were in closer, so that could be why the gas giants are out that far. We're going to look at an image here though this is a movie that was taken, or images that were taken from the Juno spacecraft that's actually flying around Jupiter right now. So this spacecraft has been there for, I think, 6 years now, 6 or 7 years. And what it does is it flies in close to Jupiter, snaps a whole bunch of images, captures a whole bunch of data, and then flies out again because it can't stay in orbit around Jupiter. The radiation being released by Jupiter is so strong that it would fry the electronics on this spacecraft. But look at the images that we're seeing of Jupiter here. That's a painting right there. I'm just amazed every time I see these videos. And you can find these if you go to Juno Spacecraft, it's called. Go to YouTube and you can see the number of times that it's cycled around Jupiter. And it's still there doing many more close approaches. We'll see the great red spot appear here very shortly. You can look at the the intricacy in those cloud tops there, ammonia and everything else. There's a great red spot. Jupiter's by far the largest planet in the solar system, more than twice as massive as all the other planets combined. Jupiter's familiar stripes and swirls are actually cold, windy clouds of ammonia and water floating in an atmosphere of hydrogen and helium. Jupiter's iconic Great Red Spot is a giant storm bigger than Earth that has raged for hundreds of years. Jupiter also rotates about once every 10 hours, but it takes about 12 years actually to go around the Sun. It's a gas giant, and so it lacks an Earth-like surface. If it does have a solid inner core at all, it's likely only about the size of Earth. Let's play that one more time. Jupiter's atmosphere is made up mostly of hydrogen and helium, and 9 spacecraft so far have visited Jupiter. 7 flew by, and 2 have orbited the gas giant, and the most recent one actually arrived in 2016. That was Juno. That's the one where these pictures are coming from. Jupiter has more than 75 moons. I think the count is up to 79 now, I believe. And it does have a very faint ring system as well. Jupiter, Saturn, Uranus, and Neptune all have rings. Of course, Saturn's are the most glorious of the bunch because they reflect so much light back. But okay, let's go on from there. Where are we going to go next? I think next we're going to take a look at these guys. So these are the 4 Galilean moons. These are the 4 moons that Galileo discovered back in 1610 when he took his little telescope and pointed it towards Jupiter. Noticed that he knew where Jupiter was, and Jupiter was a planet. The word planet is the Greek word for wanderer, so we knew that these worlds wandered around the sky. They didn't stay stationary like stars do, so we knew that Jupiter was that world. But we didn't know what was near it like this. We call our moon the moon because we didn't know there were any other moons. Galileo was the first to see 4 moons orbiting another planet, another world. And these are the 4 that he saw. So what happened was I believe basically he went out and saw Jupiter, saw these objects around it, witnessed the fact that they had moved over night after night, and was kind of puzzled. You know, he knew the stars didn't do that, so he actually was witnessing a mini solar system, really, when you take 79 moons counted up. But these 4 worlds here are the most inviting ones. There's Io, covered with sulfur mostly, and it's the most volcanic world in the whole solar system. Actually, there are several active volcanoes right now on Io, and we flew the Voyager spacecraft by that and witnessed an active volcano when Voyager flew by there in 1979, I believe. Europa, that's the most fascinating one to me because that is a shell of anywhere between 8 to 12 kilometers thick of ice, but underneath that ice we believe there's a global-sized ocean. And the reason why we believe that is because it looks like a cracked eggshell, and those cracks are really water that's releasing up to the surface and freezing again, and gives us this view. We're going to be sending a spacecraft out by that called the Europa Clipper shortly, which is going to go out and snap a lot of images of Europa, get us more high-definition images that we've had before. These ones were captured by Voyager as well. The 3rd moon out there is called Ganymede. That's the largest moon in the solar system, also covered with ice, and we believe there's a saltwater ocean underneath that. And it's actually large enough, it's bigger than Mercury, Ganymede. And if it was going around the sun, it would actually be called a planet. It's that big. And then we've got Callisto, the most heavily cratered moon in the whole solar system. So these 4 are the beauties of Jupiter, and those are the 4 that you can witness easily through binoculars or a telescope, small telescope. So very fascinating worlds to discover. The reason why there's so much sulfur and stuff on Io though as well is because these 4 worlds do not go around Jupiter in a circular path. They orbit Jupiter in an elliptical path. And as they do, then they get farther away from Jupiter and then closer as they come in and move around. And when they do, they actually move. They stretch and skew a little bit. They change their shape, I'll call it, a little bit. And that's enough that it causes friction. That friction releases material, brings it up to the surface, and that's what causes these volcanoes. And of course, probably what causes this global-sized ocean down here as well. Now, at the bottom of our oceans, there's life that's never seen sunlight. Could there be life at the bottom of the oceans of Europa? That's the biggest question right there. That's the world there that fascinates me to know when to see whether or not there's going to be something happening when they discover things with Europa. We may never drill down through the surface 8 to 12 kilometers, but there may be other ways that we can find out what's there. Jupiter does come to opposition this year as well. Of course, we're going to catch up to Jupiter. It takes 12 years to go around. There's what opposition means again. It's the Sun, Earth, and Jupiter all lined up. And Here's a chart that I found for oppositions of Jupiter over the next number of years. So here we are in 2022. So September the 26th is when we're going to get Jupiter at its finest. A couple of weeks before and a couple of weeks after that, that's when they'll be lined up. So sun sets, Jupiter rises, sun rises, Jupiter sets. It's up all night long. The best viewing, it's up. It's at its highest point it can be. So watch for Jupiter in September this year. And there again, there we are with our drawing. So already rotating counterclockwise. Here's Jupiter way out here though. So what's happening now? We see Earth, Venus, Mercury. Venus, Mercury, and Mars, and then the Sun comes up, and then Saturn and Jupiter. Well, we have to keep rotating around, and once the Sun goes down, see there's the Sun going down right over there. Follow that line down. There's Jupiter. What does that mean? That means that Jupiter is in our evening sky. So the sun set first before we could see Jupiter. So Jupiter is in our evening sky. So there it is 6 p.m. And it's getting closer and closer to the horizon because we're moving around. We're moving around this way, and Jupiter is going to be behind the sun here shortly. So is Saturn. Saturn is getting behind the sun there now. It's almost. We're going to see that in a second. Okay, next one out, Saturn. Sixth planet from the sun, second largest planet in the solar system, adorned with thousands of beautiful ringlets. Saturn is unique among the planets. The ringlets are made of chunks of ice and rock, some as big as my fist, some as big as a refrigerator or even a car. None of the ring systems are as spectacular, as complicated as Saturn's though, from all the giant planets. Like fellow gas giant Jupiter, Saturn is a massive ball, mostly of hydrogen and helium. 9 Earths side by side would span across Saturn's diameter, so it could fit 900 Earths inside of Saturn. That doesn't include the rings though either. 1.4 billion kilometers away from the sun, Saturn takes about 10.7 hours to rotate on its axis once. A Saturn day and 29 Earth years to orbit the sun. About 2 tons of Saturn's mass actually came from Earth. The Cassini spacecraft that was intentionally vaporized in Saturn's atmosphere in 2017 made Saturn about 2 tons heavier. There's actually a hexagonal storm that sits here on the North Pole of Saturn, and it's a storm that's shaped like a hexagon. It's the most amazing thing, probably the most unusual storm in the whole solar system. Saturn has 82 moons, and it actually has some little moons called ringlets, or moonlets, shepherd moons, that actually push in and push out on the ring system and keep them in line. The ring system is going to disappear probably within the next what did they say? I think it was 100 million years. The rings will disappear. And some parts of the rings are actually disappearing now, but the moon Enceladus of Saturn, we'll see that in a second here. I'm going to take a look at a couple of the moons of Saturn. A couple of the famous ones. Titan is one of the most famous. It has organic compounds on it. It has lakes of liquid methane. Here we were able to strip away the clouds because we were never able to do that from Earth. But Cassini was able to do that for us. We actually landed a small probe on Titan called a Huygens probe. I'm going to stop there for a second. And the Huygens probe came down through the atmosphere of Titan, landed on its surface, and we had images all the way from the cloud tops right down to the surface. We could see these huge lakes of liquid methane on the surface. And when it landed, there were these large boulders that were completely round. So we know that there was liquid flowing on the surface of Titan. But very cold. Enceladus is the next, probably the next most fascinating world out there of Saturn. Take a look at here in a second. Should come right up. And Enceladus is another frozen world with lots of cracks on its surface. We believe as well underneath Enceladus' ice is another global-sized ocean. We actually took Cassini and flew by Enceladus. And when we were flying by, there were geysers that were spitting up into space, and we flew through the geysers and tasted them, basically, and we registered water. So we know there is water coming up from the geysers of Enceladus. And partly, as well, it's kind of cool is that Enceladus's geysers, we believe, are responsible for replenishing the ring system. So what Saturn's rings lose as parts of those materials spin off into space, Enceladus's geysers replace that, replenish the ring system. So pretty neat. Views of Saturn change every time that we look at Saturn. because it has such a magnificent ring system, we don't think about this, but Saturn is tilted at about 26 degrees. So as we come up to Saturn each year, it's in a different location as it on its path around the sun. It takes 30 years, of course, so each time we come up to Saturn, we see it differently. And here we can see what happens with that view is that the rings actually change in our perception of the rings from our point of view. So they'll be at a point when they'll almost disappear completely, and then we'll start to see the top of the ring system. So we're going to go down here to 2022. Here we are here. We still get a pretty good view of the rings this year, but we can see next year they're going to start to disappear. And over the next couple of years, they'll almost disappear completely. So we'll have a very, very thin ring with Saturn by 2025, but then they'll start to open up again with our best views down around 2029. So that does happen with Saturn. We do get our views do change quite a bit. Again, with Saturn, there's our drawing again. I'm not going to get into too much. We're in 920 now. So as we move around here, counterclockwise again, here we are, a few planets in the morning, then the sun comes up, and then we've got Jupiter in our evening sky, but you can see the sun and Earth and Jupiter are almost lined up here. Saturn, sorry. So Saturn is coming up to Superior Conjunction when it's going to be behind the sun from our point of view. Now, when that changes and Earth moves around here faster, that means that Saturn's going to be up in our morning sky. So it will appear in our morning sky shortly after Superior Conjunction. This is Saturn in opposition. Opposition for Saturn this year is going to be in August the 14th. So that's when Saturn, Earth, and the Sun, Earth, and Saturn are lined up in a row. Sun sets, Saturn rises, Sun rises, Saturn sets. And this is our view from Earth this year. So, nice little chart. There again, our view of Saturn. So as I mentioned, Saturn is going to be at Superior Conjunction, which means it's on the opposite side of the sun from us. But as we go around the sun faster, counterclockwise, Saturn takes a little bit slower of a path. That means that Saturn's going to pop up in our morning sky. So we'll have Venus, Mars, and Saturn, and Mercury here for a little while, about the first week of March. So we'll have the four planets in our sky first week of March. A little bit about Uranus. I'm not going to talk too much about this one. Uranus is the coldest world in the solar system, really. It actually sits on its side. It's tilted at a 90-degree angle with respect to all the other worlds. It has a really nice ring system. We did pick that up with Voyager 2. It's also has huge clouds. Uranus is the seventh planet from the Sun. Third largest diameter in the solar system. It was the first planet was found with the aid of a telescope. It's about 1.8 billion miles or 2.9 billion kilometers away. Uranus takes about 17 hours to rotate once and about 84 Earth years to complete an orbit of the Sun. It's an ice giant. We call it an ice giant because it has ice in its atmosphere. Uranus and Neptune are called ice giants. Jupiter and Saturn are called gas giants. Water, methane, and ammonia mostly, all above a small rocky core. Uranus has an atmosphere made mostly of molecular hydrogen and atomic helium with a small amount of methane. Uranus does have 13 known rings. The rings are narrow and dark, and the outer rings are brightly covered, and Uranus has about 27 known moons. Well, let's move from that one to our view of Uranus in the sky. Uranus is way over here, so we've rotated around our morning sky. We're into our evening sky, all the way through our evening almost, and then we see Uranus late in the evening. So let's take a look at where Uranus is right there. There we are, February the 1st at 8 o'clock at night, and it's fairly low at 8 o'clock. So we can't see it till very late, and you can only pick that up really with a telescope. A small telescope will reveal a very tiny green ball, but even in one of my largest telescopes, it's very difficult to see because it's so far away. Neptune. Neptune's next. A little bit about Neptune. Dark, cold, and whipped by supersonic winds, the ice giant Neptune is the 8th and most distant planet in our solar system, more than 30 times as far from the Sun as we are. Neptune is about 4 times wider than the Earth. Neptune takes about 16 hours to rotate once and about 165 Earth years to go around the Sun. It has 14 known moons. And this huge spot coming up here called the Great Dark Spot, that is a large cyclone on Neptune that we've seen just with Voyager 2 spacecraft, first time that was ever visited by a spacecraft. Neptune in the sky, same thing. Here we are again with our drawing. There's Neptune here, so we would see Neptune before we would see Uranus in the sky. And Neptune is closer to the horizon. Uranus is up here. Pluto. Talk a little bit about Pluto. Everybody wants to know about Pluto. What happened to Pluto? Why isn't Pluto a planet? Well, I still call it a planet. Always was when I was a kid. But anyway, a little bit about Pluto. These are images from the New Horizons spacecraft that went out and got our only images ever of Pluto. From Earth, even with the Hubble, we just saw a very one pixelated dot. We can see here that Pluto was covered with ice. It's a dwarf planet in the Kuiper Belt, we call it. It's a donut-shaped region of icy bodies out beyond the orbit of Neptune. Pluto, which is smaller than Earth's moon, has a heart-shaped glacier. This fascinating world has blue skies, spinning moons, mountains as high as the Rockies, and it snows, but the snow is actually red. It has 5 moons. Pluto orbits the Sun at about 5.8 billion kilometers away on average, about 40 times as far from Earth, in a region called the Kuiper Belt. Now, a year on Pluto is 248 Earth years. A day on Pluto lasts about 153 hours, or about 6 Earth days. And Pluto is about 2,380 kilometers wide. That's about half the width of Canada, or 2/3 the width of the Earth's moon. Pluto has 5 moons of its own. The largest, Charon, is so big that Pluto and Charon orbit each other like a double planet system. Now, what happened to Pluto as far as the Pluto story goes? Well, a few years ago, some astronomers got together and said we have to make a decision on what we're going to call a planet, because we started to find other worlds, Ceres, Eris, that were larger than Pluto, and even our moon is bigger than Pluto. So we think that there are, well, we discovered about 400 other dwarf worlds now that are out in the Kuiper Belt, and we believe there could be up to 1,000 more worlds that are Pluto size or larger out past the Kuiper Belt. So where do we stop to say, okay, that's a planet now? So they had to lay down, the IAU had to get together and decide what is a planet. So first of all, they said the planet must orbit the Sun. Can Pluto orbit the Sun? Yes, it does. Really oddball path, kind of a rogue kind of a planet, not in the same plane of the rest of the planets, but it is a planet. Second up, it must be large enough to be round. Well, Phobos and Deimos, they're not round, they're asteroids. So it has to have enough gravity to pull itself into a round shape. That's what they're talking about. And is Pluto a round ball? Of course it is. It is large enough to make itself a round ball. Thirdly is where it lost out, though. It must dominate its orbital zone or clear out other sizable bodies as it orbits the Sun. Well, we've seen our map here earlier of the Earth with the number of potentially hazardous asteroids that pass through our path as we go around the Sun. And we are about 1.7 million times as large as any of them. So we can clear them out of our path if we wish to on their way around the Sun. Well, Pluto is only about 0.07 times the size of the object that passed through its path as it goes around the Sun. So that's where it lost out. So Pluto then became a dwarf planet along with Ceres and Eris and I mentioned up to 400 others now, I guess. So anyway, I still believe he's a planet. Not gonna let me down. Okay, but is that all the worlds we know about? Of course not. We're doing a lot more discovering. We're looking at finding locations elsewhere, many exoplanets. We're finding them by different means. Here we are back in 1992 when we only found a few of them using something called radial velocity. And what that meant was that you've got a sun and a planet, and we watched that sun wobble back and forth a little bit, and that's because a planet is tugging on it. So that's something called radial velocity. That was the first ones that we found. Then we saw ones called using the transit method, which meant that we had a star with a small planet passing in front of it, and that light would dim a little bit as that planet passed in front of that star. Then we have imaging ones that we picked up, and now something called microlensing, which means that as that sun has warped space-time, basically, and light can be bent around that star while we can image the planet worlds behind them. So here's how things have improved. There's 2014, 2015. You can see the large clump there up on the top left-hand corner. This is the Milky Way, of course, spread out in different ways so we can see them. Uh, 2019, 4,003. We're up to over 6,000 worlds now that we've discovered as far as exoplanets go, including several systems that have several planets in those systems, including the TRAPPIST system, which is going to be taking center stage here very soon with the James Webb Telescope. It's going to be looking at the atmospheres of the worlds around TRAPPIST-1. Here's our sun, and this is the only place in our galaxy that we've looked so far for exoplanets and found over 6,000 with about another 7,000 candidates that are out there that we haven't yet qualified as being planets, but they're candidates. So we believe there's still a whole lot out there. Let's take a quick look now, coming into the end of it now. Going to show us a little bit about the scale of what we're talking about when we look at all this stuff. So let's look at our moon. This is a little YouTube video I've seen a number of people use before, but I kind of like it. So we're going to do a comparison here between our moon. There's Mercury, slightly larger than our moon. Mars, bigger than Mercury. Venus and Earth, slightly larger than Venus, but almost our twin. Here we go out to the gas giants, into Neptune. Work our way into Saturn. That's without the ring system. And then Jupiter, the last massive planet. All the other planets would fit inside it, but that's nothing when we compare it against some stars. So here's our sun. On scale, we've already lost the Earth way off the scale altogether. Our sun is not the largest star at all. There's Sirius A. There's Pollux, just one of the stars of Gemini, the twins. Arcturus, we see that in our evening sky, the arc to Arcturus from the Big Dipper. Red giant star Aldebaran in Taurus, that's visible right now in Taurus. Rigel, the bottom right-hand star of Orion. The Pistol Star, the blue hypergiant. Now we're getting into some really big stars. Antares A, red supergiant. Mu Cephei, a red supergiant, and then what was the largest star out there, VI Canis Majoris, and that was just a couple of years ago. But now it has been replaced by a larger star even than that again. So let's take a quick look. We're going to take our spacecraft, we're going to fly in over the top of that star, and we're going to take a look at what the size Earth would be in comparison to that star. That would be us right there. $1.3 million Earths would fit inside our sun. I can't imagine how many would fit inside that one. But they did calculate that if you were in an airplane flying around VI Canis Majoris, it would take you roughly 1,142 years to make one trip around VI Canis Majoris. 1,142 years. I'm getting to the end, I think, pretty close. And I forget what this is now. Just a second. Oh yeah, we're going to look at some nebula now. I don't know if you can hear the sound in it. Just a second. Might be able to. No, not going to hear sound, but we're going to take a look at. Oh yes, we will. There are things out there, of course, a lot larger than our solar system, and we're going to talk about these actually some of these this week. But there are things called nebula, which are large clouds of dust and gas that form stars and other systems, and I want to compare some of those with you to look at some of the scale that we see. So here's our solar system at 0.0006 light years across, and we'll start there. I love those scales of things. They really do make you feel pretty humble, I'd say. Humility really gets to you when you see that kind of stuff, and like this. Here's the galaxy on the right-hand side of the image is IC 1101, and that's in the Abell cluster, 29 galaxy cluster. It's the largest known galaxy in the universe, and it contains about 100 trillion stars. Milky Way, IC 1101. And just a quick look here at a spot that the Hubble Space Telescope imaged. We know the Hubble has done an amazing job to change our perspective of the universe. Would be a piece of sky that would be about the size of a grain of sand held at the end of your arm. Hubble stared at that one spot in the sky for over 10 days with its lens wide open, and the longer the lens was open, the more light it was able to capture. This is the image that it saw in a spot of sky where it thought it was completely black. This image has over 10,000 galaxies in it. Each one of them has over 100 billion suns in it. So that's the size of a grain of sand held at the end of your arm. So you can imagine how many galaxies there really are if you took that and stretched it out over the whole spectrum of the sky. And that's the same image. So, do any stargazing? Well, we'll quickly look at that. Some of the things I might suggest if you're going to get out this time of year, nice clear winter sky, be sure you bring along some comfortable blankets and a coat, even a comfortable coat, because it does get cold. Even, I know it's winter, but even in the summertime, a nice clear evening in the summertime can get a little bit cool because you're standing in one spot too. You're not really generating a whole lot of heat, so you're not moving around a lot, so your body temperature will drop a bit. And I recommend a good blanket, always good to throw in the back of the car. Nice pair of warm socks, nice cup of Java, whatever would suit you for your hot beverage, and a nice comfortable chair. The more comfortable you are, the more you're going to enjoy the experience. Of course, binoculars are very simple. Most people can have those. They're portable and lightweight. They give you the correct image. They're easy to hold, and they're not very expensive, so you can pick up a pair fairly cheaply. If you're into camera viewing, lots of great night sky views to capture. When we are looking at the sky, though, at this time of year, people have said to me that the stars seem to be a whole lot brighter around now than they are in the summertime sky. And that is kind of true because in the summertime, we're looking back this way towards the center of the Milky Way. We're looking back, of course, into this, we're 100,000 light years across and we're 26,000 light years out. So we're seeing the light from 25,000 light years of stars this way, plus the bulge, plus 50,000 light years that way. When we look back into the wintertime sky, though, we're only looking back into the Perseus arm, and behind that is all dark. It's black. It's black, dark space. So here we are here on an edge-on view. This is our summertime sky, and this is our wintertime sky. So summertime, we're looking downtown New York. We're looking at the big glow of the center of the galaxy, back into Sagittarius, and all that kind of light that we see that kind of clouds our view a little bit. But in the wintertime sky, we're looking back into deep space, and so we have the sky is blacker, and the stars are closer to us, so they're brighter. So we have bright stars, black background, contrast is better, sky looks better. This is the glorious view of Andromeda. Don't expect to see that through a telescope or binoculars. This is more like what you're going to see. This is a view through my 10-inch Dobsonian reflector telescope. So a little bit of a blown out core. You can kind of see a little bit of dust lanes there around Andromeda. That's the light from 1 trillion suns, but we can see galaxies, but this is what we expect to see. Excuse me, photons of light are instantaneous. These photons that we're seeing from here left there 2.3 million years ago, traveled through space and ended up on your eyeball when you're looking through the eyepiece. Just happened to be that those photons landed on your eye at that time. But photon light is instant light. We can't capture that light. Not with our eyeballs. We can't store photons on our eyes, but you can store them, of course, on a chip of a camera. So that's why we get these glorious views with Andromeda like this, and this is what we see through the telescope. But this is a captured view, and this is a live view. So those photons left there 2.5 million years ago and traveled all the way through space just to end up on your eyeball. It's an awful shame about how many photons actually come out here, and no one gets to receive them on our end. So that's something to think about. And of course, programs like Stellarium are the best for looking at the night sky or preparing to look at the night sky or looking at what you'd like to see in the night sky for the next time out. Have a look at this though. While you're reading this right now, you're traveling at 1,600 kilometers per hour as we rotate once on our own axis. You're traveling at 107,000 kilometers per hour as our planet revolves around the sun. You're traveling at 70,000 kilometers per hour as our solar system travels in the direction of the bright star Vega. You're also traveling at 792,000 kilometers per hour as our solar system rotates around the Milky Way galaxy, which takes us 250 million years. And you are traveling at 2.1 million kilometers per hour as our galaxy travels through the universe in the direction of what's called the Great Attractor. We are all space travelers. Catch us tomorrow night at 8 p.m. Atlantic time on the Sunday Night Astronomy Show. We'd love to have you tune in. I hope you enjoyed tonight's presentation. It's been a lot of fun for me to bring it to you. Nice to get by a little bit nasty night. Well, the nasty night looks like it's all over with now, but thank you very much for joining me. It's been a real pleasure to bring this to you. Again, the program will be up. It's recorded, so you can see it on YouTube or Facebook later if you want to have the kids sit down and watch it. Or these are the type of presentations that I offer through school systems as well, or through Brownie groups or Girl Guide groups or whatever. I can customize the presentation based on the group. I've got probably 75 of them prepared right now. I change out a few slides to keep them current, that kind of thing, but I really enjoy the opportunity to bring everything to you. So thanks very much, everybody, for watching. There's my Christmas present if anybody wants to put me down on their Christmas list, or go fund me page. There we go. Anyway, I hope you all have a great evening. Thanks very much for tuning in. It's been a real pleasure to bring this to you. Take care, everyone. Clear skies, and keep looking up.